In today's lesson, we're going to be looking at simplifying radicals. So this is a lesson from Algebra B, but due to COVID, and I know some of you might have missed this information, we're going to go ahead and take a day and practice these because you are going to use these in Geometry B. So in today's lesson, what you're going to be doing is you're going to be simplifying radicals, which is pretty much the square roots. In Algebra B, you guys did some cube roots, but we're just going to look at square roots for right now. You're going to be simplifying them without decimals. So if we take a look at this first one's really nice because 25 is a perfect square. Now you might know the answer, but I just want you to remember, when you take the square root of something, you're really asking me what number times itself gets to 25. So you can't say like 1 in 25 because that's not the same number. So it has to be exactly the same number. So it would have to be 5 times 5. Or it could actually be -5 times -5. So when you take the square root of 25, technically it's plus or minus 5. So all of these answers should have a plus or minus on them, but I'm not going to worry about those because you guys are going to be transitioning into geometry. And let's be honest, when you're dealing with a triangle, if this was a 3, a 4, and you had to find the side, you would run Pythagorean theorem. So you'd go 3 squared plus 4 squared is equal to x squared. And then you would go 3 squared, which is 9, 4 squared is 16. You would add those together and you would get 25 is equal to x squared. And then you would take the square root of both sides. Now, the square root of both sides, the square root of 25 is 5. But that is not going to become a -5. So we don't have to worry about the negative radicals when we are in geometry. So again, I'm going to drop this plus or minus for right now. When we look at number 12, the problem with number 12 is there's no exact number that multiplies. If you're thinking 6 and 6, that's 6 plus 6, not 6 times 6. And the other thing is if you grab your calculator and you try to type in the square root of 12, you're going to notice that it's what we call irrational. Where if we do the square root of 25, it's what we call rational. So this is nice, this is rational, this is irrational, because look how bad the decimal is, okay? So what do we do with ones like this that don't have the same number? So what you want to do is you want to think of multiples of 12. So you want to think of the multiples of 12. So you might be doing this in your head. So it would be like 1 times 12, or maybe 2 times 6, or maybe 3 times 4. Those are the multiples of 12. Now, what combination has a perfect square in it? So if you don't know your perfect squares, that's going to be one of the first problems. So let me write down perfect squares. So basically what I want you to think about is like 1 squared is 1. 2 squared is 4. So then 3 squared would be 9. So 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, and let's just do 10 squared. This right here, these numbers are perfect. Okay, so we need to be looking for a perfect number out of these combinations that we have. And so if we go, neither one of these two are perfect, so we're going to ignore those. Neither one of these two numbers are perfect, but the 4 is a perfect number. So what we're going to do is we're going to write down 3 times 4. And then the square root of 3 is quite ugly. Again, it's irrational. So if we take the square root of 3, look how nasty that is. But if we take the square root of 4, because 4 is perfect, look how nice it is. So what we're going to do is anything that's what we call irrational, we're going to leave it underneath the symbol. When it's perfect, we're going to actually take the square root. So the square root of 4 is 2. So if I were to show you a comparison, again in my calculator, the square root of 12 compared to the square root of 2 square roots of 3. So do you see how those look physically different, but yet they're exactly the same value. So sometimes this can be a little confusing because people will say like, well, why are we doing this? Kind of go back to your late elementary, middle school days when you first started to learn fractions, like let's say 5/10. You learned that both of these numbers are divisible by 5, and so you could reduce this to 1/2. Well, these look different, but if I were to type them in my calculator, we all know that they have the same value. So basically, we're doing the same thing with radicals. These look different, but yet they have the same value. So I really compare simplifying radicals to simplifying fractions. Over time, if you continue on with math, you'll find that these won't be as weird for you. You'll be more comfortable with them. But this is the answer that they're looking for. So let me try one more with you and then I'll have you pause it. So 18, you should be thinking of the combinations that multiply to get 18. So obviously 1 and 18, you'd have 2 and 9, and you'd have 3 and 6. Those are the different combinations. This one does not have a perfect square. This one does. This has no perfect square. So we want to be using the combination of 2 times 9. 2 is irrational, so we're going to leave it under. And then we actually take the square root of 9, which is 3. So then this would be our answer, okay? So why don't you pause it here, and you can actually try all the way up through 7. I didn't even notice that. There's 2 7s. So I want you to kind of stop after this one. I'll have to fix that if I use this again. So stop after this one right here, okay? All right, hopefully you paused it. So 20 would be made up of 4 times 5. And the square root of 4 is perfect. Whenever it's perfect, that comes out of the symbol. And when it's not perfect, like the square root of 5, you leave it alone. So that would be our answer. 45 would be 9 times 5. So again, the square root of 9 is perfect, so that's a 3. The square root of 5 is quite nasty, so we'll leave this one alone. Now 32, I bet that there are some of you that have the wrong answer for 32. I mean, I can't see your paper because obviously I'm not with you right now, but 32 is divisible by 4. Actually, you know what? Let me grab a separate sheet of paper because this is not going to be fully right. So 32 is divisible by 4 times 8. I don't disagree that 4 is not perfect, so this is a 2, but the problem with 8 is 8 also has a perfect square inside of it. So if you think of 8, that's also 4 times 2. So this gets a little messy because you've got this 2 out front. When you take the square root of 4, you get another 2. And then this one is stuck underneath the symbol because it's irrational. So then sometimes it's like, well, what do I do with these? This is really 2 times the radical symbol. So these are 2 times 2. So the answer is 4 square roots of 2, okay? This would sort of be like reducing a fraction, but not reducing it potentially like all the way. And again, if I gave you a really easy example, let's say 4/16, okay? We know those are divisible by 4. But let's just say somebody they're divisible by 2. So you would write down 2/8. That's technically not wrong. It's just you can go lower than this. So you need to continue on and tell me 1/4. So if you didn't recognize at the beginning that they're divisible by 4, then it's going to take you longer to get to the correct answer. So what they wanted you to notice is that 32 is also made up of 16 times 2. 16 is also a perfect square, just like 4 was a perfect square, but there's nothing inside that. So the better option is to use 16, I guess is what I'm telling you. The square root of 16 is 4, and then you can't do anything with the 2. The larger perfect number that you can find, the easier the problem is going to be. All right, the first number 7, you should have been using 49 times 3. So the square root of 49 is 7, and then you can't do anything with the 3, so you just leave it in there. Okay? Now, and the last ones here, we're just kind of getting into some twists and turns, and so I just wanted to kind of walk you through some of these because, again, remember when we have Pythagorean theorem, if I was to change this 3 right here, if I was to redraw this triangle and I was to put a square root of 3 and then I had a 4, when you do Pythagorean theorem, you have to know how to multiply this out. So I want to practice that with you. So remember, a square means that you actually repeat the symbol twice. So it's like the square root of 6 twice. So that's really the square root of 36. And then when I take the square root of 36, I get 6. So some people might say, does the square cancel the symbol? Yes, it actually does. Just be careful when you get one like this. So let me just show you the long version and then I can show you the shortcut again. So you're going to have 3 square roots of 5, essentially, times 3 square roots of 5. So if we multiply 3 times 3, and then if we multiply radical times radical, we get 25. And then if we take the square root of 25, we get 5. And again, some people are like, what do I put in the middle? Remember, there technically is a multiplication symbol sitting there. We've just dropped it. So it's really 9 times 5, which is 45. So what ends up happening here is this square cancels the symbol, but you have to be careful because many people will write down 3 times 5. I don't disagree that it cancels the symbol, but you're forgetting that it also needs to be distributed. So then technically this should be a 9. And then now you'll get the same answer. You might be saying, well, why didn't you do that over here? Well, because there was a 1 sitting out front. Yes, I'm distributing the square to the 1, but 1 squared is still 1. And then the square cancels, and so I get 1 times 6. So it kind of is a difference. Do you have a coefficient out front or not? Okay, so that makes a difference. If we go to the next row, we just notice we don't have a square, but we have a number sitting out in front of that radical, okay? So the number sitting out there is just kind of sitting there, but remember, there's a multiplication sign. Now what you want to do is you want to break down the square root of 27 using the same technique as we did from the row above, or like from this problem. So you need to think what multiplies to get 27, that one of the numbers is perfect. So that would be 9 times 3. So we have this 2 out front. When we take the square root of 9, we get 3. And then this guy is irrational, so we leave it alone. And then now we just multiply this out. So 2 times 3 would be 6. And then that would be my answer. Okay? Why don't you go ahead and pause it and just try number 10, and then we'll talk about 11 and so on. Okay, hopefully you paused it. And if you work this out, you got the 5 out front. 8 would be 4 times 2. We already kind of talked about that one when we did the 32. So we've got an 8 right here. So we've got the 5. When we take the square root, we get a 2. And then this one is irrational, so we leave it alone. Remember, every time I say irrational, basically what I'm telling you is if you were to type in the square root of 3, look at how nasty that is. But if I type in the square root of 9, look how nice it is. Rational, irrational. Those are the vocabulary words. So same thing here. If I type square root of 4 versus square root of 2. When it's nice, it comes out. When it's ugly, it stays underneath. Okay? So then my answer would be 10 square roots of 2. And again, if you want to know if you're doing this right, you can type them in. So you can say 5 square roots of 8 and then 10 square roots of 2. Now, for some of you, this might look weird because it's the first time you're doing it. But it's just like when you learn these reducing fractions. The more you do them, the more comfortable you'll become with how they look. This does not bother me one bit because I've been doing it for 20 years, okay? All right, we only got a couple more to go. Number 11. This is just straight multiplication. So we're just going to multiply what's underneath. So we're going to go 2 times 22, which is 44. And then now we just have to reduce the 44. So you have to think of what multiplies to get 44. Think right away, ooh, these 4s are perfect. So can I take 44 divided by 4? And that's a prime number. So that's really, really helpful. When you get prime numbers, that is probably, I would say, the best case scenario because you know they're not divisible. It's when you come out with a non-prime number, a composite number is the word I was looking for. When you come out with a composite number like this, you don't know if it's divisible by anything. So that's where it can be kind of a problem. All right, so the square root of 4 is 2, and then you get square roots of 11, and then you're done. So why don't you try 12? All right, hopefully you paused it. You should multiply these together, and so you get 120. Now you got to think of what multiplies to get 120. So it comes out to be 4 times 30. And right here is the good example. We can tell that this is 2, but the square root of 30 can be challenging because just like we saw the square root of 8 was irrational, but there was a perfect number inside it. The square root of 30 is irrational, but is there anything inside of it? So what you should be saying to yourself are, what are my multiple combinations of 30? What is every combination that will get me to 30? 3 times 10. I think those are all my combinations, right? Do any one of these have a perfect number? No, 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 no. So then this is done. Again, this can be challenging because this is called a composite, where this is prime, prime, prime. Those are easier to see. All right, let's try 13. So 13, the only really difference with 13 is now you got this 2 sitting out here. So there's a 2 there. Technically, on number 12, there was a 1 and a 1 sitting there. It's just 1 times 1 is 1, so we just got to ignore it. But now, because there's a 2, we can't ignore it. But 2 times 1 is still 2. And then we're going to go ahead and do 7 times 14. And I don't know that off the top of my head. And I get 98. Now, I know 98 is divisible by 2, but I'm kind of worried, will there be a larger number or something? So what I would do if it was me, if I'm looking at the number for 98 and I have no idea what the multiples are, 98 falls right here. I highly doubt it's divisible by 81 because they're just too close. But what about 64? So if I go 98, and if you're not sure, divide it by 81 and you'll see, okay? So 98 divided by 64. Nope. What about 98 divided by 49? All I'm doing is going through the list. The reason why I started on the high end is because if I start on the low end, I might have a hidden. So you want to start on the high end. And look at that. 98 is divisible by 49. So I know that this should be 49 times 2. So I've got this 2 out front, and there's a multiplication sign there. The square root of 49 is 7. This is irrational, so it stays under. And then I multiply those together, and I get 14 square roots of 2. So why don't you pause it? This is your very, very last one, and let's see how you did. Okay, hopefully you worked it out. You go 5 times essentially 1, and then you're going to go 18 times 3, and I already worked that out. It was 54. And then I've got the 5 out front, and then I knew 54 was 9 times 6, so still carrying the 5 down. And then the square root of 9 is 3, and then the square root of 6, again, this is a composite, but 6 is only made up of 1 times 6 and 2 times 3. Those are the only options. And neither one of these are perfect, so I know that the 6 is done. There's nothing else I can do. It's kind of like, again, if your teacher gave you a fraction and you, and let's say it was 5 over 7. There's nothing they're divisible by. So then, you know, or what if I gave you, how about 10 over 21. Well, this is divisible by 5 and 2. This is divisible by 7 and 3, but they're not divisible by the same number. So that means this is done. Kind of the same way here. So our answer is 15 square roots of 6. So I hope this gives you a little bit of review from Algebra B, and I hope this will be helpful in your Geometry B class.